This lecture is going to be about presenting your data in a visual, organized way, otherwise known as graphing, and talking about why scientists use graphs and charts to display their data and easily communicate what their findings are to other people. So, the first reason that we use graphs are because it gives us a really quick visual idea of what happened over a series of experiments or investigations. So it's much easier to visually see a picture and get an idea of trends or patterns than it is to, say, read a paragraph or a couple of pages of conclusions and analyses. In some cases, that can be really time-consuming and a little bit confusing, more often than not. And so the graph gives us a way to just see the data and get an impression about what happened over the course of the investigation. It also shows us rate, or how something changes with time. It might be a temperature change over time. It might be a speed. It could be length or velocity. Time tends to be a very common variable in most sciences, and we often like to see how things adapt or evolve from the beginning of a certain time period to the end. So, the most common graph that we will use in chemistry is a line graph. It looks something like this. I'm sure you're familiar with line graphs. And the situations in which we use line graphs is whenever we have a manipulated variable, which you always put on the x-axis. Whenever we have a manipulated variable that is either constant or continuous. So again, when we're talking about rate, time is a continuous property. It goes on and on and on at a predictable speed or rate or unit. So time is very commonly one of our manipulated variables. We always put our responding variable on the y-axis. We generally start both axes at 0. And if 0 is not an appropriate place to start, let's say we're measuring height as our responding variable over a period of time, and our smallest height measurement is, say, 100 centimeters. And it goes up to, say, 1,200 centimeters. We would like to be able to show both the low point and the high point in an evenly spaced way. And so maybe it's not appropriate to start this graph at 0. Maybe it would be more appropriate to start this graph at, say, 50. And so in that case, we start our graph and we draw a little kind of lightning bolt shaped line to show that we have skipped from 0 to some other value, and then we set our bottom point at 50. That's just a for instance. Okay, some of the other important details, we're going to get rid of that, shoot that over there. Some of the other important details are the way that we identify our graphs. So, again, let's make our generic line graph over here. We always need to have a title for our graph. So let's say height over time, for instance, if we're using our same example from last time. Then anybody who's looking at this data immediately knows what the data is representing. It represents a change in height when compared to time. We always, well, that's not what I meant to do. We always need to label both axes. So again, this was height. I'm going to abbreviate. And maybe it's in centimeters. So you label it with a name, and then you label it with the units. And then our other axis was time. And again, let me label that, let's say, in seconds, perhaps. Although height doesn't generally change by the second, but who knows? Maybe in this case it does. So we always need to have a title. We always need to have axes that are labeled and units that are obvious. Otherwise, the graph's really not very useful to anybody. The final thing that we need to do is to accurately show the pattern as much as possible. So let's say that we have a data set that looks like this. we've got, sorry, I'm making crazy things here. We've got a data set where here's our first point, here's our second point, here's our third point, there's our fourth, there's our fifth. So that's how our height changed over time. Now, the inclination a lot of times is to connect the dots, which is not really an appropriate way to show a pattern in science. It's more appropriate to show a line of best fit. So that line can either be in a curve, if your trend is somewhat level at the beginning and then increases sharply, or that line can be in what's called an average line of best fit, where we draw a trend line that shows the pattern in our data in an average sense. So here we're showing that the data increased, the height increased over time at a relatively steady pace. That's what that information would indicate. Okay, let's move that, and we'll get back over here. So when we see this line of best fit, this red line here, that can give us the slope, or how much change occurred over time, which is a characteristic that you will often use in science. Next slide, here's another example graph of when you have multiple trials. And again, this computer program connected the dots, which is not appropriate. You would include your 3 different trials. They use 3 different colors, which is great. They also use 3 different shapes to represent each data point, which is also great. But what they should not have done is connect the dots as they did. Instead, you would draw a line of best fit like we just talked about, and it would look something like that. So it would be the average of all of the data sets, and it would show a trend. There are also a couple of problems with this graph in that there is no title. It needs a title like rainwater in May, perhaps, right? And then it also needs to include labels on each axis. So over here we should have days of May or something to that effect, and down here we should have hours of rainwater collection or something like that. At hour 1 we had this much rainwater, at hour 2 we had that much rainwater. And so it's important to make sure that we identify what's happening. Oh, I think I said days in May over here. That's kooky. That's not what I meant to say. I meant to say volume of rainwater collected after 1 hour, after 2 hours, after 3 hours on 3 different days in May. So disregard my days. Getting a little loopy today. All right. So we talked about different lines that you might see, trend lines, and we generally refer to these lines in the shape that they show us. So linear, again, is when your line is straight and consistent. If that straight and consistent line goes up from 0, so it's trending upward, that's called directly proportional. So that means as this variable increases, this variable increases, and therefore the trend line increases. Sometimes what you'll see is a graph that's straight but looks like that. That means that as your manipulated variable increases, your responding variable decreases. So that relationship is called inversely proportional. And in some cases, there is no pattern, in which case we would just say there is no pattern. So here are a couple of examples, again, of direct and inverse proportions. Once again, we are missing labeling on our axes, although we have some very basic titles, so that's good. This type of graph is called a bar graph. It's probably one that you are very familiar with, and it's best used for situations where the manipulated variable is not consistent. So in this case, we have test scores for, say, one class in science. Joe's test score has nothing to do with Bob's test score, which has nothing to do with Mary's test scores, which has nothing to do with Susan's. They're all completely independent of one another, which is why they're separated. So you see their individual test scores over time, but there's no line of best fit or any proportional relationship because the manipulated variable is not a consistent or trending variable in this case. Over here we should definitely have a label on our axes, scores by percent. Okay. Last two graphs we're going to talk about, we are going to use almost never, so we're going to fly through them. The first one is a pie or circle graph. And again, we need to have these labeled. There should be percentages here. So for instance, our brown might be something like 45%. And it looks like these other three are pretty close to the same. So let's say maybe 17% and 17%. And I don't know what that would be. That would leave me with about 21% or something. And so we can see each of those different characteristics. We use a pie chart anytime our data is a fraction of 100%. So if you want to know out of an entire school how many people want pizza for lunch, or out of an entire country how many people are going to vote for the Republican candidate, then you can put that into a pie chart so it's an easy comparison to see out of a whole group what part of the group feels this way or that way or has this characteristic. And we really don't use that very often in chemistry. The final graph type is a scatter plot. This is when you have huge volumes of data. So in this case, we're looking at income, say, in, Pierce County, for instance. And we want to know how many families in Pierce County have an income of these different values. So 2 families have this income, this many families have this income, etc. And then we can see where there are groups of data. What number of families has the highest income? What number of families has the lowest income? You can easily compare the average income, what income occurs most frequently, things like that. And again, this is not something that we will use very often, but it is important and valuable to know how it works. So that is the end of our conversation about graphs and data presentation, and we'll be doing a whole bunch more practicing on this as we go forward. Thanks very much.